My name is Peter Krampusch. I am a research professor at the University of Dunaújváros, which is one of the smaller universities at my home country, Hungary. The research project, the result of which, or some of the results of which I will present to you, it's a large one, dealt with high-performance materials in the automotive and the power industry, and that portion which I present to you is just a small part. Actually, the research itself was done by one of my PhD students, who is Balázs Fekete, and all the other colleagues, either in the Czech Research Institute, in Hungarian Academy of Science Research Institute, were involved for various aspects of the investigations. So what was the motivation of the work? We were dealing with the structural materials of the reactor pressure vessel in Russian-designed nuclear reactors. Hungary operates 4 units, and the units are in the age of the life extension, which is not a fashion in the world, but it's a rational tool. The goals of the investigations were to investigate the kinetics of the fatigue process and developing energy-based models behind the well-known Coffee-Manson model. Why to deal with the fatigue kinetics? Because there are quite well-known models of the Western type of reactor materials. However, in the literature there are much less knowledge on the Russian structural materials. And because I told you the units are operating at the moment beyond the lifetime, which was considered by the designers, the operator needs to know more about these materials. We investigated 2 types of materials. One is a chromolybdene vanadium alloyed benitic steel, which is the pressure boundary of the vessel, and the other one is a quite well-known chrome nickel alloyed titanium stabilized austenitic steel, which creates the anti-corrosive cladding of the reactor pressure vessel, and this material is the structural material of all the reactor internals. We produced cylindrical specimens with 8 mm diameter and 7 mm length, and we tried to simulate the operating conditions, and low cycle fatigue can occur in the reactor pressure vessel during heating up and cooling down, which belong to the normal operation, plus sometimes during some accident conditions. And we performed isothermal low cycle fatigue experiments and thermomechanical experiments. Strain controlled fatigue was done, and the equipment which were used for the fatigue experiment was a Global thermomechanical physical simulator, which is not a material testing machine. However, it can be equipped or could be equipped quite well to do the experiments. It's just a picture about the experimental layout with the specimen here. Some results of the low cycle fatigue. This is the total strain amplitude versus the number of cycles, which is the traditional presentation of the results. And you can see the bainitic material and the austenitic materials. There are some difference between the between both isothermal and thermomechanical fatigue. It can be said that both materials showed a lower life in the thermomechanical conditions, but this 15H to MFA is more sensitive to the thermal cycling than the austenitic one. We investigated the fatigue kinetics. We have made TEM and the transmission electron microscopy in various stages of the fatigue life. That shows here an initial state, and it is a bit later, which is about 50% of the fatigue state. And then in this graph you can see the evolution of the dislocation density, which was calculated in the various stages. They are just, these pictures are just illustrations. We made it in more precise stages. And you can see this quite interesting first increasing, and later on as the fatigue is progressing, then it's, I wouldn't say saturated, it's even decreased. And that is the austenitic material, where the initial stage showed its nice distribution of the dislocations, and later on, again in the 50% of the fatigue life, you can see the cell structure, and then we also calculated or measured the dislocation density in each stages, and then here you can see this curves. Here we were able to distinguish between areas where the dislocation density was poor and then in rich, and then we had the total. So the total shows a quite stable or saturated progress or process. We made scanning electron microscopy or on the specimen fractures and fractography on the fatigue crack surfaces. And then you can see here some example. This is the surface of the specimens when the total strain amplitude was 1.5. I'm not sure that it is good visible, but you may see some network of the initial cracks on the surface, and then there is the fracture surface all in the isothermal fatigue. And then that is in this picture, you can see the fracture surface near to the starting position of a crack. And then we try to analyze the striation lines as a consequence of the fatigue on the length of the crack, and here you can see in this small graph, and then these figures are the total strain amplitude here. It was the fractography and the fatigue kinetics, and then we were dealing with the energy-based low cycle fatigue model. And the mechanical basis is as follows here. The strain energy once the cycles have been stabilized, can be expressed by this equation. And we propose that the fatigue toughness to start of a crack propagation can be determined with the number of cycles to start of the crack propagation as it is seen here. So, and then the proposed new model is deals with to quantify the critical amount of stored energy required to introduce to into the material to the failure. And is it written in this equation where the beta is the Taylor-Queenie parameter and the D and the delta are the fatigue toughness coefficient and the exponent. And then some illustration of this energy-based model. And you can see here the stored strain energy, this W stored to fatigue, and the cycles, and you can see both the isothermal and the thermomechanical fatigues curves are quite well. In the case of the austenitic steel, this is the picture of these two curves. We try to compare the prediction capability of the low cycle models, which we considered, and then we put here the well-known Coffin-Manson models, and then which I did not show the results, but we, of course, we evaluated the results based on this too, and also the energy-based models, and you can see in both materials investigated, you can see a quite well correlation between the total strain amplitude versus cycles and the energy-based criteria. Quickly the conclusions. The microstructural changes related to the observed mechanical behavior. We performed dislocation density measurements, both by calculation on the TEM pictures plus with X-ray diffraction, and the course of the dislocation density and its dependence on the usage factor was similar for both steels. At the beginning of the cyclic loading, the total density increased and then gradually decreased with increasing number of cycles. However, the nature and distribution of the dislocations of the individual steels varied, and this resulted in the different mechanical behavior of the two type of steels. Macro cracks form nets on the small cracks and plastically deformed strips at sites where the slip bands cross the surface of the test specimens. The distances between the striation lines initially increased with an increase in crack lengths and then became saturated. You remember this small picture in the corner. And an energy-based model on the low cycle fatigue prediction model based on strain energy was developed as an attempt to account only the part of the strain energy which is stored in the microstructure and which causes the fatigue damage. There was another part of the work which was not included in the presentation because of the time limitation. And then I refer here is only the part. It means that we were able to separate those energy which generated the heat in the specimens during the fatigue process. This model, this energy-based model, had no limitations and could be applied for the reactor steels investigated under both the isothermal and the thermomechanical conditions. Thank you very much.